Good morning, everyone. So welcome to my YouTube channel, Mathsastram. So today we are going to see 17th lecture on Riemann integration. So let's start today's session now. So today we are going to prove a result that if a function f is bounded on closed interval AB, if the set of points of discontinuities of f on closed interval AB has finite numbers of limit points, then such type of functions are Riemann integrable. Let f closed interval AB to R be a bounded function. If the set of points of discontinuities of f has finite number of limit points, then f is Riemann integrable. It means f belongs to RAB. Okay. So its proof is simple and depends on the last lecture's theorem. Okay. Let the set of points of discontinuities of f has limit points W1, W2 up to WL. Okay. Finite in number. Okay. Finite in number. Okay. Now you see that this is closed interval AB. You have W1, W2 up to WL. Okay. These are the limit points. If you take epsilon neighborhood of these points, closed interval, any closed interval which contain more than one element, then you take intervals, closed intervals around these limit points. So all the points of discontinuities will be inside these intervals except finitely many discontinuities. Because what is the definition of a limit point? Limit points means you take any neighborhood of such points, all the points will be inside it except finitely many. Okay. For example, it means there are finite numbers of limit points. It means there will be that many sequences which approach to whose limit is these points. Okay. So if you take any epsilon neighborhood of these points, so after a certain stage, all the terms of the sequence will be inside these closed intervals. Okay. So finitely many points of discontinuity will be outside of these subintervals. Okay, which contains W1, W2, WL. Okay. So we enclose these intervals by y1 z1 y2 z2 yl zl. Okay. Okay. So let epsilon greater than 0. Choose points y1 z1 y2 z2 yl zl belongs to closed interval AB such that y1 is still less than z1. Okay. z1 is still less than y2. y2 is still less than z2. Like that. Okay. yl and zl. Okay. zl. Okay. And W1 contain in y1 z1. W2 contain in y2 z2. Okay. And so on. WL contain in YL ZL. With epsilon j goes to 1 to L mj minus mj zj minus yj. Okay, that is less than epsilon by 4 because function is bounded. Okay, so we can choose y, j and zj so close that this quantity is less than epsilon 4 by 4. Okay, let's say this equation number 1. Okay, now what is closed interval AB? Closed interval AB is nothing but union of A y1 union y1 z1 union y2 z2 union z1 y2 union y2 z2 union z2 y3. Okay, union y3 z3 z3. Okay, and so on, and it is okay. It is y it is ZL minus 1 YL union YL ZL union ZL B. Okay. Okay. We have settled down these intervals Y3 Z3 like this. Okay. By taking this summation. Okay. We are taking this closed interval, the length of this closed interval, Y1, Z1, Y2, Z2 closed interval. The length is positive. Okay. Length is positive. Length is positive, and W1 lies in between. W1 lies between in between. So that is why I am going to write this here open interval, because this points lies in between. Okay. So it will be more clear then, because we are taking positive length of this, and W1 lies in this open interval, W2 lies in this open interval. Okay. And this is happening. So these are the limit points. These are the limit points. So observe that, note that you see these intervals A1, Y1, okay, and this you consider Z2, sorry, and this is Z2, Z1, Y1, Y2, okay, and this is Z1, this is Z2, Y3, okay, and then ZL minus 1, YL, okay, and last interval is ZL B. Because all the limit points is enclosed by these intervals, this type of intervals, Yj, Zj intervals. So these intervals will contain at most finitely many points of discontinuity. So these intervals. Each interval, each subinterval contains only at most finitely many points of discontinuities of F. Okay. Discontinuities of F. Okay. So in equation number 1, we are taking epsilon by 2 here. It will be better. Okay? Epsilon by 2. We are taking epsilon by 2 here. Okay, no problem. So we were here, and each subinterval contains only finitely many points of discontinuity. Otherwise, each point in these subintervals is point of continuity. Okay. So by theorem of lecture 16, by theorem Riemann integration lecture 16. We have f belongs to R A y1 because f has only finitely many points of discontinuities here. Okay. Similarly, f belongs to R A y. F belongs to R Z1 y2. Okay. F belongs to R. Similarly, here also has finite points of discontinuity. Z2 y3. Okay. And so on. F belongs to R ZL minus 1 YL, and finally F belongs to R YL B. Okay. Because function is bounded on a closed interval AB, and these are the subintervals of closed interval AB. So F is bounded also on these intervals, as well as these points contain only finitely many points of discontinuity. By the theorem in previous lecture 16, these functions will be Riemann integrable on restricted on these subintervals. Okay, that is why these functions are Riemann integrable on these intervals, subintervals. Okay. Okay. So these functions are Riemann integrable over these subintervals. Okay. So choose partitions P1. Okay. Choose partitions 1, P2, P3, P3, PL and PL plus 1 of AY1. Okay. Y1 Z1 Y2. Okay. Z2 Y3 ZL minus 1 YL and YLP respectively. Okay. It means P1 is partition of this, P2 is partition of this, P3 is partition of this, and last one is partition of this respectively, such that U P P J F is minus L P J F is less than epsilon upon 2 L plus 1 or J goes to 1 to up to L plus 1. Okay. Now put P is equal to P1. Okay. P1 U1 union Y1 Z1. Okay. Union P2 union Y2 Z2. Okay. Union and so on. Okay. Union Y L minus 1 Z L minus 1 union PL. Okay. Union Y L Z L. Okay. Union PL plus 2. Okay. Okay. Then what is this? Then what is this? This is nothing but A. Okay. A Y1 Z1 Y2 Z2 and so on. YL minus 1 ZL minus 1 YL ZL. Okay. G. Okay. Then from equation 1 and 2, we have UPF minus LPF is equal to summation J goes to 1 to L plus 1 UPJF minus LPJF. Okay. Okay. Plus summation J goes to 1 to L. Okay. It will be equal to capital MJ, small mj, zj minus yj. Okay. Now this is less than, inside thing is less than, so this will be less than summation J goes to 1 to L. This is epsilon upon 2 L plus 1, 2 upon L plus 1. And this is already less than epsilon by 2. This is less than epsilon by 2. Okay. So what you got? So this is epsilon by 2 L plus 1. Okay. Summation J goes to 1 to L plus 1 plus epsilon by 2. We are adding 1 L plus 1 time. So it is 2 L plus 1. Okay. Into L plus 1 plus epsilon by 2. So this will be cancelled out. Okay. So this will be cancelled out. So this is epsilon by 2 plus epsilon by 2. So that is epsilon. Okay. So this implies UPF minus LPF is less than epsilon. Okay. So what we have given epsilon greater than 0, there exists a partition P of closed interval AB, okay, such that, okay, so above we should write P is a partition of AB. So we take union here. So this implies P is partition of closed interval AB. Okay. So here P is a partition of AB. So given epsilon greater than 0, we got the partition of AB such that UPF minus LPF is less than epsilon. This implies F belongs to RAB. So F is Riemann integrable over closed interval. Okay. Now we will see one example. Is the function F Riemann integrable over closed interval 0, 1, where F at 0 is 0 and Fx is 1 upon 2 to the power n. If 1 upon 2 x lies in between 4 and 0, 1, 2, okay, and so on. So let's see its solution. So Fx, if I am taking x in this range, 1 upon 2, then what is this? This is 1, okay, and this is 1 by 2. If x is in this range, 1 upon 2 square, okay, and this is what Fx is equal to 1 upon 2 square if x lies in between, okay, and so on. Okay, so last one is what? Fx is equal to 1 upon 2 to the power n if x lies between, okay, and this is going so last one is f at 0 is 0. This is 0 if x is 0. Okay. you see that starting from below at 0 it is 0. Okay. Then you will come somewhere here. It is giving 1 upon 2 to the power n value. Okay. And then in this interval, its value is increasing 1 upon 2 square. On next interval, it is giving 1 by 2 and it is 1. So you see that this function is monotonically increasing. This function is monotonically increasing. Okay. Observe that f is monotonically increasing. Okay. Monotonically increasing on closed interval 0, 1. So this implies f belongs to R closed interval 0, 1. That is one fact. That is one fact. By this you can check that function is Riemann integrable. Okay. Another fact. This was the one fact. Another fact. We will use our theorem. Another fact. We will use our theorem. Okay. So tell me how many points of discontinuities are there. You see that at 1 by 2, the function is discontinuous here. Because in this interval function is continuous and suddenly at 1 by 2 value is 1 by 2. So here on 1 by 2 it is discontinuous. Here on 1 by square it is discontinuous. Next 1 upon 2 cube it is discontinuous. So what are the points of discontinuity? Points of discontinuities of f are 1 by 2, 1 upon 2 square, 1 upon 2 cube, okay, 1 upon 2 to the power 4, 1 upon 2 to the power n minus 1, and 1 upon 2 to the power n, and so on it is going on. Okay, concept. You note that function is continuous at 0. Why? Function is continuous at 0. Why? Because if you take sequence converging to 0, it will fall somewhere 1 upon 2 to the power n plus 1 is to be less than x, less than equal x is less than 1 upon 2 to the power for some natural number. Okay. And what will be the value of corresponding that sequence will be fall in this interval. The corresponding value of will be 1 upon 2 to the power n. So sequence is approaching to 0. Every time the functional value is decreasing and it is decreasing to 0. So function is continuous at 0. But function is discontinuous on these many points. Okay. So what is the limit point of these points? So this point, so this set has limit point. This set has limit point. What is the limit point here? Where this sequence is converging to 0. So 0 is the limit point of discontinuity. Okay. Therefore, 0 is the only limit point of set of discontinuities is What is set of discontinuities? 1 by 2, 1 upon 2 square, 1 upon 2 to the power n minus 1, 1 upon 2 to the power n, and so on of f. Okay. Here, such limit points are finite in numbers. Such limit points are finite in number. Therefore, by theorem, we have f is Riemann integrable. F belongs to R. So, by another fact, that was the main point of our theorem, we proved that f is Riemann integrable. If you want to show that this is Riemann integrable by monotonically increasing fact, you can also do. Okay. So that is another fact. So that is one fact, and another fact, by using the points, set of points of discontinuity of f, set of limit, the limit points of set of discontinuities are finite in number. So therefore, this function is Riemann integral. Okay. So that is one fact. Okay. And another fact is this monotonical increase. You use any fact, you can show that f is Riemann integral. One fact is that it is monotonically increased, that is why it is Riemann integral. Another fact is the set of points of discontinuity has finite numbers of limit points, that is why it is Riemann integral. Okay. You can use any one. So this function is Riemann integrable. So answer is yes. This function is Riemann integrable. Okay. So answer is yes. Yes, this is Riemann integrable. Okay. So today's lecture up to this. If you have any problem related to this, you can comment on my YouTube channel. Like, share, comment, and subscribe my YouTube channel. We will see you in next lecture. Thank you very much.